Welcome to Durable State of Persistence, where we cover storage-related topics in the container ecosystem. My name is Eric Forget, and this is episode 1, Orchestrator Basics. Before we take a deep dive into container storage concepts, I'd like to provide a high-level overview of orchestrators. An orchestrator, or more formally a container orchestration system, allows users to declare their intended state and then works to implement it. Examples of container orchestration systems include Swarm, Kubernetes, and Marathon. Quite often, I'll use the term orchestrator, container orchestration system, and cluster all interchangeably. We'll give an overview of container orchestration system and provide some examples of how users interact with them. We'll talk a little bit about the availability benefit that we get from these declarative systems. We'll talk about storage volumes and how storage volumes interact with this availability benefit. And then we'll quickly talk about storage access modes. The format that we're going to use to explore these topics is a set of simple diagrams that work kind of like a comic book. So each cell is going to essentially show a step in the process. Across all the diagrams that we have today, the bottom layer here is showing the cluster, and these are the nodes that make up the cluster or orchestration system. The user really doesn't care about these nodes. The orchestrator essentially abstracts these individual hosts or nodes such that the user no longer has to worry about where they want to run a workload. They just declare to the cluster, I want this many of this type of workload, and the orchestrator takes care of scheduling and maintaining that number. So these colored boxes are my workloads, and these could be containers. Some orchestrators could be groups of containers, but this is the workloads that are backing my application, and the color is the different application. So I've got a new application that I want to run on my cluster, and it's this light green application. And so what I'm going to do is declare that I should have one of these running on my cluster. As you might imagine, the cluster will see this change and then accommodate it by creating a new green workload. And the cluster is going to find the best place on the cluster to run this new workload. Obviously, creating new workloads is interesting, but we can also edit workloads. So I may decide that I want 2 yellow because I've got customers that are complaining about latency, something along those lines. And so I declare to the cluster, I want 2 yellow, and sure enough, the cluster accommodates my request and eventually starts a second yellow. Once I'm running this second yellow for some time, I can decide I don't need it anymore. And similarly, I can say, hey, I don't want that yellow anymore. I only want 1. And then the cluster is going to remove 1 of the yellow. Right? This was running previously. Now it's not running in my cluster. And again, I'm just saying how many I want. I haven't called one of them yellow 1 and the other yellow 2, and then I have to go and say, hey, stop yellow 2. All I'm saying is I want 1. So again, this is just a high-level overview of orchestrators. We've only scratched the surface here. There's far more complex things that you can do and changes that you can affect. Popular ones are upgrades, blue-green rollouts. Depending on the container orchestration system you're working with, there's many more options. This, again, high-level generic view of how we interact with clusters. So an interesting benefit of this declarative nature is you get some amount of availability for free. So let me show you what I mean by that. So here, one of my nodes has gone away. Hardware failure, somebody stepped on a network cable, and with it, it's going to take two of my containers. So the declared state right before this incident was that I wanted 2 light blue and 2 dark blue containers. And so the cluster is constantly trying to maintain that. So when a node goes away, the cluster may or may not care about the node, but what it will realize is that it no longer has 2 light blue and 2 dark blue, and it's going to remedy that by starting a new light blue container and a new dark blue container. The containers that we've been talking about so far are ephemeral workloads. What that means is that the data that's written to the file systems within the container is not going to be available when these containers start on other nodes. So in this case, where I was running on this node, the information, any information that these containers wrote to their local file systems is not going to be available when we restart them on other nodes. When we want to have stateful workloads, and by stateful I mean those workloads that are going to store application information, we need to introduce the storage volume. And what we've done here is I'm going to declare that I want a white workload to be started on the cluster, and it needs to have a volume. And this storage volume is going to be where we store the application data that should be available no matter where a white workload starts on my cluster. The first step that the cluster is going to take is going to be to attach the storage to the node that it intends to run this container on. And then, just like before, we'll see that the container starts and the volume is mounted within the container, and that is associated with this volume. Again, because our cluster is constantly looking at what's running and what should be running, in the case that we lose a node, and it doesn't have to be as dramatic as losing a node, an administrator may need to take a node down to add more memory or do maintenance on it. And so this might not be as dramatic as a node failure. This might be an administrator that says, hey, drain this node of workloads because I need to work on it. In any case, the workloads here are going to go away, and the cluster is going to have to remedy the situation. So in this case, what we'll see is that our volume gets attached to a different node where the orchestrator is planning to run our white workload. And then we'll see that our white workload ends up with the volume and it's running. And of course, the green workload, light green workload, ends up being rescheduled as well. Right? The cluster's maintaining this. The key here is that anything that the white workload wrote while it was on this node into this volume is now available here. So if this was a MySQL database or Postgres, something like that, you would want the files that make up the database itself on the volume, and we've just provided essentially a level of availability to our database without having to do active standby or any of those older tricks to providing availability. All right, so let's talk about access modes. So far what I have described is something that we call single writer access mode. Single writer means that one node, that's the single, one node has read-write access to a particular volume. Now, on that node, you could have any number of containers that are accessing that volume, but the access is limited to one node. The second type is multi-writer access mode. And what that means is I can have multiple nodes simultaneously do read-write to a particular volume. And the third is multi-read-only access mode. So the first example that we're going to show here is the single writer access mode. And I want 3 workloads. Again, these could be containers, they could be groups of containers, but I want 3 of them to all have access to the same volume. And so I declare that to my cluster, it is going to look at the access mode and realize that it is single writer access mode. So it's going to attach the volume to the node. And then my containers or my workloads can start, and they'll all have a view of the volume from within the container. This single writer access mode is most often used with a block device and very commonly with a file system that is a kernel mounted file system, such as XFS, EXT, that sort of thing. The reason that we want to have this limitation is that because it's a kernel mounted file system, the kernel essentially owns the metadata and doesn't expect any other kernel to be manipulating the metadata. In fact, if we took a file system that's mounted on this node and we also mounted it on another node, that kernel is going to make the same assumptions and write to the metadata, and we would end up with a corrupted volume. So that's why the single writer access mode is important to specify in this use case. So let's talk about multi-writer. And I've got the same type of declaration. I want 3 of these things. I all want them to have access to the same volume at the same time. But this type of volume is defined as a multi-writer access mode, and what that means is that the cluster could run the workload on multiple nodes. And so in this case, my storage has been attached to 2 of the nodes, and as you might expect, I can now have my workload running on 2 of these nodes, and these containers then have access to the storage. The difference is that we won't use a kernel file system in this case. More often this will be an NFS or CIFS, a NAS protocol, where the metadata is actually owned by the device itself and not owned by the individual kernels. And since that metadata is control is centralized here, that's why we can mount this on multiple nodes. All right, thank you for watching. Hopefully this was interesting, if not educational. Stay tuned.